Hello, this is a integrity recording on the topic of partition analysis, as it's known in JUMP. It is also more commonly called classification and regression tree analysis. And this is both an exploratory method and it's also a statistical modeling technique. And the origins of this method go back to the late 1970s at Stanford, where some statisticians were looking for a very general way of doing statistical modeling that could deal with messy data, could also deal with a large number of predictors, and was relatively easy to do. And the result of that was something called CART, which they also trademark. They are also very savvy business people who have their own statistical consulting company. So JUMP uses the term partition analysis, and rather than do a lot of explanation of it, it's often easier to explain it simply by demonstration. CART modeling, again, is a statistical modeling technique used to explore relationships between some response of interest and possibly some large number of potential predictors of that response. And what we call CART or partition modeling is a common and popular method used by people in data mining and the emerging field of predictive analytics. We will not delve into all details of CART. There are quite a few. It is relatively easy to understand, however. And if you want to learn about this and many of the other emerging methods of statistical modeling, then I suggest the course we teach at the University of New Hampshire, Math 738, 838, in predictive analytics and modeling would be a good choice. Doesn't require a lot of background to take it, and we'll talk a lot about the underlying basis of CART. But in this example, you'll see how it works. One of the nice things about partition analysis or CART is that the predictors can be continuous and they can be categorical, and likewise the response can be continuous or the response can be categorical. This is a really easy to use model. As an example, spam filters are built on CART models, and also things in healthcare like risk analysis can be done with CART models, where we might build this CART model to predict for a patient who's been admitted, what's the probability they might experience a fall. And again, falls are a serious liability for most hospitals and healthcare facilities. So the way it works, I have a response, I have some number of predictors, I look at each one of the predictors. If it's continuous, I look across its scale of measurement and I start partitioning it into two halves. And then I try to find a partition that explains the biggest difference in the response between the left side and the right side. And if it's continuous, the response is continuous, then it would be the one that this split would occur where we see the biggest average difference between both sides. And because we're doing this on a computer like JUMP, it'll look through all the continuous variables and all the potential cut points, and then it will pick the variable and the cut point that explains the most variation in the response. And it does this by the biggest average difference. For categorical predictors, it simply looks at all possible combinations of them. In other words, it looks at all possible splittings and then finds the split that again shows the biggest difference in mean response. If your response is categorical, such as you might say the risk a patient falls or they do not fall in a hospital. So for these particular cases, what you do is you find the splits that give you the biggest difference in probability between the two, and by the way, there can be more cases. So that's the basic idea. And again, I'm going to mostly demonstrate this by example. And again, the idea is we look through all the potential predictors, we find ways to partition their scale of measurement in such a way that it explains the most variation in the response, and we measure their ability to predict the response in terms of something JUMP calls a log worth. There's also another statistic that it's called a G squared. Again, at this level, we will not delve into the details other than the larger the log worth, the more variation is explained in the response. And again, partition modeling can be used simply for exploration, and it can be used for statistical modeling. I have found myself in a consulting practice that CART modeling is often the first place I look when I'm trying to get an idea of what potential factors or predictors might be most closely related to the response. And in fact, I have found in many cases, even in complicated scenarios, partition or CART modeling has quickly gotten us to focus in on the right small set of factors that are the best predictors of the response. So it's an efficient and it's a very effective exploratory and statistical modeling technique. So I'm going to illustrate CART modeling with a simple example, and this is called the IRIS data, first published by R.A. Fisher in the 1930s. And what it is, we have three species. This is our response, three species of iris: virginica, versicolor, and setosa. We then have a set of measurements on these plants, so this is data that was collected, and what we'd like to do is build a model based on the physical measurements of the plants that best predict what species it might actually be. Okay, so again, I'll illustrate this in a moment in JUMP, but I just want to show you how partitioning works. So there are three species, and what we'd like to do is look through the potential predictors. There are only four: the sepal length, the sepal width, the petal length, and the petal width. So what JUMP does, it goes through the measurement scales for these four variables and finds that petal length is the best predictor of which of the species one is looking at. It has the highest log worth value. So what JUMP is going to do is split on petal width. And basically, we won't get into this, but what JUMP did, it looked across the whole measurement scale in the data for petal length and found at 3 inches it had the greatest ability to separate or distinguish between the three classes or species. Okay. So notice what JUMP does. It takes the original data set and now it partitions it into two halves. It takes half of the data where the petal length is greater than 3 inches, that's on one side, and on the other side is the petal length is less than 3 inches. By the way, looking at the JUMP output, and by the way, these are also called tree models because when we're done, this is going to look a lot like a tree diagram. Notice if the petal length is less than 3 inches, then all the irises that are less than 3 inches are correctly identified as setosa. So that's why JUMP picked 3 inches, because it gave us the best ability to distinguish between the species, and in fact it has now definitively classified setosa. So all the setosas are less than 3 inches. But look on the left-hand side. It's 50-50 versicolor and virginica. So is it possible we could take the left-hand data, split again, and possibly find another variable that will let us distinguish between versicolor and virginica? Okay. Well, here's an example. This is a diagram of the data. And notice that JUMP picked 3 as the cut point for petal length, and you'll see it does, as we showed, separate between setosa and the other two, versicolor and virginica. Well, the next question is, on this right hand side, that is petal lengths greater than 3, is there a place we could split where we could separate between versicolor and virginica? Notice that actually somewhere around, and we'll just eyeball this, around 1.7 or 1.75 inch for petal width, we actually, if we could partition that right hand side there, we might be able to separate versicolor and virginica. So we're going to let jump do it for us, and sure enough, on the left hand side of our tree diagram, it took all the data that's where petal length is greater than 3 and broke it down into 2 parts. Petal width less than 1.8, petal width greater than 1.8. And sure enough, look at our diagram. So we now have what we would call 3 rectangular regions that are partitions of the original data. Okay, so right now we have come very close to being able to correctly identify between setosa, virginica, and versicolor. But keep in mind, if you look at the plot on slide 14, there are a few misclassifications. And in fact, it is unlikely we'll be able to completely separate the classes. And this is the common case. There's always going to be some amount of misclassification. So finally, we do one more split, and jump picks petal length at 5 inches and splits it into 2 parts. And if we look at the data, you can see why jump picked to do the split at 5 inches. So we now have 1, 2, 3, 4 rectangular regions that are partitioning the data. And notice that we've minimized the number of misclassifications. This is essentially how what we call partition modeling works. And what's nice about partition modeling, okay, it's easy to understand, and I'm going to skip to slide 19. And the way this model works for prediction, if an observation falls in a node, it simply assigns the average or the proportion for that node. Okay, so here's an example for versicolor. If the petal length is greater than or equal to 3, if the petal width is less than or equal to 1.8, and then if the petal length is then less than 5, the probability it's a versicolor is 0.98. Therefore, we just go ahead and we classify it as 0.98. So the models are really simple, and there's no really horrendous underlying theory. This is actually a very clever and very easy to comprehend method, and as I said, widely used and popular among data miners. So let's quickly look at the data, and I'll show you how to do it in JUMP. So go to the Analyze menu, Modeling, and then select Partition. So our response is categorical, it's species, and then an X will put in our 4 predictors. Okay. And in the main report menu, once you're at the report window, in display options, I recommend pick show split probability. Okay. So here are our candidates, and as we saw earlier, jump is going to split on petal length. Okay, so notice again it classifies the setosas correctly. Then we'll split again. Okay. Notice the next split, where we split on all observations where petal length is greater than 3. Notice that this does a pretty good job. 90% of the observations in the left-hand side are versicolor, almost 91%, and on the right-hand side, 98% are virginica. So we could really stop right here, but we could try one more split. And notice, again, it splits on the left-hand side. So what it's trying to do is on the left-hand side to see if we can even better refine the difference between versicolor and virginica. So if it's less than 5, the petal length less than 5, the way you would read this, by the way, first petal length is greater than 3, petal width less than 1.8, and then petal length is less than 5, 98% are versicolor, and if it's greater than 5, then about 67% would be virginica. But notice in the layer above, we've already gotten a model which separates virginica. And then at this point, there's some things you can show. A leaf report is a compact way to show you all of the pathways to get to each of the terminal nodes in the tree. And there are 1, 2, 3, 4 terminal nodes. Okay. And if you want to, you can actually save the prediction formula, which I will not do. You can actually see it in the notes. So that gives you the basic idea of what's called partition analysis and how it works.